Stochastic Analysis and Critical Theory workshop, and especially warm welcome to everyone to the first day of the workshop from perturbative to non-perturbative QFT. So yeah, we had these two workshops where we noticed there's quite some overlap, so we decided to try this out to have both workshops overlapping. So today will be a mixed day with topics from both. And we start the morning with Viet Dang and 5 to the 4 and 3 dimensions measures on compact Riemannian manifolds.
Okay, so first I would like to thank the organizer for the very kind invitation. I'm very, very grateful to them for inviting me here because I'm not expert in SPD and I'm amateur in QFT. Okay, so I will report on joint work on the construction of 543 measure on compact Riemannian manifolds together with Dang, who is here, a colleague at Sorbonne University, Ismaël Bailleul at the University of Brest, and Léonard Ferdinand, who is going to talk this afternoon, who is based in Orsay. Okay, so let me start by introducing smoothly what it is all about. So I'm going to mimic Margherita's talk yesterday. I'll start from a spin system. So you have a discrete finite box that is represented by this rectangle. And on each lattice side, you have a vertical rod. And on each vertical rod, you have a mass, which is represented in red, and the masses are connected by springs. The configuration space of your system are maps, sigma, from the discrete finite box into R. And this you can identify, of course, with vectors in R to the power lambda. And given this configuration space, we define an action functional. So the action functional is a sum of two parts. The first part is a discrete Dirichlet energy. So you recognize the discrete Dirichlet action, and a polynomial in the spin sigma I, which I call the interaction. Okay, so following a long tradition in quantum field theory. Okay, and if you want to understand intuitively what is the meaning of the interaction, in this case, you can think that on the vertical rod, my daughter, she has put some glue, and it becomes an inhomogeneous vertical rod, and the mass has a tendency to stay longer in this position here and in this position here that correspond to the bottom of the wells of this interaction potential. So this kind of interacting potential sometimes is called Alencane in the math literature. I mean, we saw it yesterday. Oh yeah, Mexican had potential. Okay, so the important we are going to be interested in is the Gibbs measure. So you take exponential to the power minus the action, you mod out by you divide by the partition function, and what you are interested in is to define or make sense of correlation functions. So you are given a k-upple of points in your discrete box, and you consider the product sigma I1 times sigma I2 times sigma ik, and you average with respect to the Gibbs measure. And this average is called a correlation. So, okay, you are going to ask, okay, so here, I just want to make a very short digression. Why are we interested in such systems? They are called ferromagnetic in the literature. So here are among the 3 big stars of ferromagnetic systems you encounter in books. So you have a configuration space, as I described. So in the case of the Ising model, is plus minus 1 to the power lambda. And in each of these cases, the Ising model, the discrete F model, and the Ginzburg model, so the one we are interested in is Ginzburg-Landau, the density defining the Gibbs measure has this sum over neighboring spins plus sigma I, sigma j. And the fact that you have a plus in front of the interaction between neighboring spins tells you that the system has the tendency to have all the spins aligned in the same direction. So it is called ferromagnetic, from what I understand. Okay, and okay, so now I just would like to to tell you why, in fact, why are we interested in this Gibbs measure? What makes it so special? So one of the things that we learn in a quantum statistical physics textbook is that, in fact, the Gibbs measure is a solution of a variational problem, okay? So let me tell you or recall what this is about. You consider the partition function, and if you take minus log of the partition function, so this is called the free energy. So it is like in Razvan-Gouraud's talk, you take the minus log of this guy called the free energy, and for every probability measure, you would like to compare the free energy, and you would like to compare this right-hand side. So let me try to tell you in words what this is. This is the average of your action under your probability measure. And this is minus the entropy of the probability measure nu, okay? So let me make a small comment. This is gonna be small when the probability measure makes the spin independent, right? And this guy is gonna be small when your probability measure charges the minimas of the action, okay? So this has a tendency to produce delta measure carried by the solution of the variational problem, and this has a tendency to make all the spin do not speak to each other, okay? So nature tries to find the best balance between these two things, and the infimum of this inequality becomes an equality exactly when the proba measure is the Gibbs measure. So I would like to thank Thomas Krajewski for the analogy with this variational principle with taxes. So you see, you have this dichotomy. If you are the state, then you can decide, okay, only the rich pay a lot, like in the situation where your probability measure charges the minima, or we all pay the same, you see? And then you try to reach a certain balance between these two conditions. Okay, so why am I telling you things about this Gibbs variational principle? Because when I started working on this, I didn't really understand why stochastic quantization gives the right answer. So, okay, I think most of you experts, they know, but since I didn't know, I thought maybe it was good to motivate why this procedure gives you a correct correlation function of quantum field theory. So this was a question that was asked to me by my longtime colleague, Gabriel Rivière, when I was very excited and told him, yeah, I'm working on 543 and all. I explained to him Feynman stuff, and then he asked me, but why does this give the correct thing? So, okay, so let's consider this operator P, which is a sum of two terms, the minus Laplacian that I'm going to call the diffusion term. So you see in the above dichotomy, this is the counterpart of the entropy, and minus the transport by the gradient of S. So you remember you have your action functional, you can compute the gradient of S, it's a vector field, and so you have the sum of these two terms, diffusion and transport, and you can define the L2 adjoint of this operator P, and this L2 adjoint, you can note that it kills the density of the Gibbs measure. So this is already a sign that this operator might be the correct one to define the QFT measure. So now we make an observation. If you have a density that solves the Fokker-Planck equation, and you plug the solution of the Fokker-Planck equation on the right-hand side of the Gibbs variational principle, then you can find, so this is a result that one can find in books, that in fact the quantity on the right-hand side of the variational principle is going to decrease monotonically. So somehow, intuitively, it means that if you use the dynamics of the semi-group described by the operator P, diffusion plus transport, then you are going towards equilibrium. You are going to look for the Gibbs measure, and we expect that at the limit, the density, which solves the above linear PDE, is going to converge when time goes to plus infinity to the Gibbs measure. And moreover, one can check by integration by parts that the Gibbs measure is a stationary measure for the dynamics of this semigroup. So somehow this, I mean, to me, this is a heuristic explanation of why this is a correct procedure to get Gibbs measure. So now one might ask naive questions like about uniqueness. So here it's a toy model, okay? We are in finite dimension. It's a discrete box, but still we want to understand things on the toy model. So we know that the set of invariant measure is a closed convex space. And we also know that the extremal points, so you see the convex, you have extremal points, they are supposed to be the ergodic invariant measure of your process. So if you are given two ergodic measures, so two extremal points, then we know they are killed by the adjoint of the Laplace plus transport. And by elliptic regularity, it means that the two measures are C infinity. And since they are C infinity, they are not mutually singular. So it means that mu1 equals mu2. So this tells you that this measure is not only the invariant measure, it's the only invariant measure because your convex has only one extremal point. Of course, it's easy, but but still it gives you some understanding of things. And the second thing is you might ask, but what is the speed of convergence? Because I say, yeah, it's going to converge towards the Gibbs measure, but what is the rate? So there is a nice result in the literature about Fokker-Planck operator, is that they are conjugate with the Witten Laplacian. I mean, I did some spectral theory and he's my friend, maybe more than this guy. And so once I saw this result, I was kind of happy because somehow it means that in this SPD business, people are doing Witten Laplacian in infinite dimension in some sense. I mean, in some sense, of course, it's heuristic. So if you conjugate, you get this Witten Laplacian, and this Witten Laplacian has a confining potential. So since you have an elliptic operator with a confining potential, so you assume that your action S has enough convexity at infinity. I don't want to be too precise, but I mean, if S is good enough, you have a kind of Schrödinger operator with confining potential, and so you expect that your spectrum is discrete with finite multiplicity. And so it means that you might have a spectral gap, and now you can recover correlators as follows. You take a random, I mean, some configuration of spin that I denote by sigma 0. You start with a configuration at time 0. You take an observable that I denote by F. It's just a continuous bounded function on your configuration space of spins. And then you take your observable, you let it evolve under the semigroup. You evaluate at sigma 0 at your configuration. You wait long enough and you converge exponentially fast to the average of F under the Gibbs measure. So you get the correlators by waiting long enough under the dynamics. Okay. And since I would like to, in the next part, I would like to go to SPDs, I need a kind of dual way to describe this evolution. So you see, in the previous slide, I was kind of very operator theoretic. I told you about semigroups, operator, but that's not gonna exist in infinite dimension. So we have to work with the process instead, whose corresponding semigroup is the Fokker-Planck semigroup. So now you consider the SDEs, du plus nabla S of u dt equals square root of Brownian. Let me comment. If you switch off the nabla of S, this is just the process which is associated with the heat equation. So it's only diffusion if you switch off the transport. But now the nabla of S will play the role of the transport in the SDE. And now if you take a solution of your SDE starting from any point, and if you look at Birkhoff averages of the observable on the solutions of this SDE, then you get, when t goes to plus infinity, the correlation. So this explains why people call this Monte Carlo time. I didn't understand. I mean, 10 years ago, I asked, tell me about ergodicity, Monte Carlo. I didn't know ergodicity, what it was, but I think this is ergodicity from what I understand. So it means that in my system, you remember with the vertical rods, the masses, It's as if I do a random kicks independently on each mass, and then I wait. So this is for intuition. Okay, now we are in D equals to 3. So my finite box is 3-dimensional, and I'm interested in knowing if I make my lattice spacing goes to 0, so the distance between the lattice point gets to 0, can I have in some sense convergence of the correlation function, okay? So it's like the UV small distance limit. And another question we could ask is there some real number gamma such that if I make a sum of the spin against some kind of spiky function at each lattice point, and if the sigma I, they are taken randomly with respect to the Gibbs measure at a resolution epsilon, gonna have a convergence when epsilon goes to 0, like in low, in some space of distribution. You know, it's like the natural question if you have a random walks, and if you rescale your random walk, and do you have a convergence in probability or in low to Brownian motion? But here, the object is no longer one-dimensional. It's not a Brownian motion. It's a three-dimensional, it's a function on a three-dimensional space. And you ask yourself, do we have convergence in some functional sense if you take this randomly, the sigma I? So the answer is yes. These are seminal results from Glim and Jaffe on the 70s, who they constructed the 543 measure on the flat space R3 on the torus T3. And in fact, even earlier, Nelson and Seagal, they constructed the P-phi2 measure on the two-dimensional flat space. Okay, so yeah. Oh yeah, it's I can explain. P-phi2 is the Ginzburg-Landau model with the P here, where P is a polynomial bounded from below. You see, this P here is a polynomial bounded from below, like phi4, for instance, is a good polynomial bounded from below. And in 2D, you have a convergence. I mean, and the convergence object is going to be a random distribution. I'm going to discuss this real soon. Okay, so here I give a non-exhaustive list of many people who contributed to this field. So it was a starting point of constructive quantum field theory, and people work on many models that I'm not an expert, so I cannot list them. I today talk about these Ginzburg-Landau type models. And but there is a major difficulty in this constructive quantum field theory business, as well as in the SPD's business, is that the things that you work with, the phi that you work with at the limit, is not like Brownian, unlike Brownian motion, which is still a function. These guys are singular distributions. So here I would like to convince you, or to give you a cheap way, to find the regularity of the random distribution just using dimensional analysis. So this is something you can find in a physics textbook. Okay, so here you have the Dirichlet action. Okay, so in physics textbooks they say action, let's say, has no dimension, dimension 0. It's a number. So this is written that way. This guy has no dimension. And you look at the integrand here. This has dimension d, length dimension d. This has dimension -1. And so you do a bit of numerology. You find that phi, the field phi, should have dimension 2 minus d over 2. Okay, just by dimensional analysis. So you expect that the GFF, so if you choose your field, you pick your field randomly under the GFF measure, so E minus S, should have regularity 2 minus d over 2 minus 0, okay? And so it means that in dimension d equals to 2, your field barely fails to be a function. It's an almost function. It's in C minus 0. And when b equals to 3, your field is in C minus 1/2 minus 0. So you see there is a difficulty in dimension 3. The field is really irregular. It's a random distribution. It's expected to be a random distribution of negative regularity. So now, yeah. It's 4. With the dimensional analysis, yeah, I got it. I got your question. you put the interaction, because here I didn't put interaction. I'm a bad student. But if you put interaction, there is a coupling constant in front of the interaction. You follow same recipe, you calculate the dimension of the coupling constant. And when the dimension of the coupling constant is 0, then they say theory is critical. What I was taught, it's like a recipe. So you put G to the phi to the power of something, and you make dimensional analysis to find the dimension of G. If it is 0, then it is said to be critical.
And it's just renormalizable.
Voilà, just renormalizable, but not super renormalizable. In my talk, this thing is super renormalizable. Okay, so now the next question is that these results from the 60s and the 70s, they hold true on flat space. So natural question, okay, more or less natural, okay? But does a 543 theory exist on manifolds? We would like to construct it on, curve background. So perturbative QFT on manifolds is a venerable subject. And it was constructed, in fact, 544 was constructed on Riemannian manifolds by Copper and Müller, also Costello. There are works by Brunetti, Fredenhagen, Hollandswald, and many other people that I didn't have the space to mention. But anyways, in all these cases, these people, they construct a perturbative quantum field theory, meaning that they work with a formal power series, okay? And so here, I have a quote from Viet Dang about the kind of difficulty. At first I thought this was done. This 543 exists on manifolds. But then I was relatively surprised when I found this quote from Viet Dang in 2021 in a survey he wrote on QFT on curve spaces. He says that if you have a theory that exists perturbatively in curve spacetime, and non-perturbatively in flat spacetime, which is the case for 543. At the time he was writing this, one would expect that it works non-perturbatively in curve spacetime. I would expect the same. Didn't need to read him. Unfortunately, not much is available in terms of rigorous theorems, except for special models like 2D CFT. And that reflects the general mathematical difficulty of understanding QFT rigorously. Yeah, I agree, it's difficult. One would think that rigorous results for a super renormalizable theory in curve spacetime might be relatively accessible, but such results are not available. So this was in 2021. So when I read this, I just looked for the literature and I tried to find what models were really constructed in manifolds, constructive QFT. So I found that the P-phi2 measure, I found some results by Dimok, and a recent result, recent, I don't know, for me, recent by Pickrell in 2007. The GFF in dimension E, is the free field, so I think no difficulty, but I couldn't even find a reference where the free field was done, but probably it is a folklore. And the Liouville quantum field theory, Liouville CFT, was recently constructed by Guillermo Rod Vargas in 2019. And this talk is about this 543. Okay, so now our strategy, as I illustrated in the toy model in finite dimension, is to try to build the 543 measure as invariant measure of this SPD. So this is like the SPD version of the stochastic differential equation I wrote for these spin systems, okay? So it's the continuum analog. And so you have this heat equation equals minus phi to the power of 3. So this comes from the interaction plus the white noise. So white noise plays the role of these random kicks, independent random kicks on the masses over each vertical rod. So of course, the construction of the 543 invariant measure from the SPD viewpoint has been investigated by many people. So here I give a non-exotic list of people who contributed to this. And I think these results were mostly on R3, on T3. And okay, I think I'm coming here 10 years late. Okay, so I think 543 was very fashionable 10 years ago in this SPD community. And maybe nowadays, okay, you guys This is all story. Now we are doing GKPZ, Young Mills, but I'm coming from the outside. And to be honest, the construction of 543 for me, I find it already extremely difficult, even from SPD viewpoint. And so maybe the point of view is different. I'm from the outside, and these papers are very impressive. And but recently, there was a very nice work by Jacklat and Perkowski, who managed, you know, by this collective behavior 10 years ago, there was this breakthrough by Martin Eyrer and Gubinelli, Perkowski, Imkeller on constructing these 543 theories on flat space. And then I think people, there are simplifications over the years by the community. And I think this paper is one of the biggest compression rate of how you can reduce the 543. I mean, it's 16 pages. I mean, the paper 10 years ago was 180 pages. So there has been, and thanks to this work, we are able to now adapt it to the manifold case. And so we are also able to treat the case of Hermitian vector bundles over your manifold. So assume you have a Hermitian vector bundle E, and you are given a generalized Laplacian on your acting on sections of your Hermitian vector bundles. So in this case, you consider an equation, SPDE, whose solutions are E-valued. So this looks like exactly like the 543 scalar version, dt phi plus p phi. This is the heat part. This is the interacting part. And here there is a twist, small twist. The interacting part involves the norm of the Hermitian norm of your bundle E plus psi E. So your psi E is no longer a white noise, it's an E-valued white noise. So you can define an E-valued white noise easily by taking a O and B, orthonormal basis of L2 of E, and you take sums over this O and B of L2 of E, weighted by independently distributed white noise in one variable. So this generates for you the E-valued white noise, and this thing is a bundle version of what is called in the literature the ON model, if I'm not mistaken. And so, yeah, sorry. E is a bundle. So, yeah, you know, the spins, they take value in abstract fibers. But anyways, you can say M times R something, and it's the same. I mean, it's the same up to, yeah.
The M here for the ON for the correspondence with the ON model
is the rank of the bundle, I think, right? Yeah, I would say so, but yeah, the dimension of the fiber. Yeah. Okay, so now you need to solve the equation graphically, as we saw in many previous talks. I think in SPD, they write nice pictures with the trees, and you know, it's like, okay. So the white noise is represented by the dot. The L, the heat operator, is represented by this vertical rod. And then when you do Picard iteration, you represent each terms as a trivalent trees. And if you start iterating your Picard scheme 2 times, you find that phi can be written as sum of 3 terms. One is C minus 1/2 minus. This is expected. This is the regularity of the GFF. In fact, the leading guy, this has the law of the GFF, minus a better guy, which is C1/2 minus, plus an even better guy, which is C1 minus. And this is something you can find by formally expanding the solution in terms of ternary trees or trivalent trees. I don't know how to say it in English, but you know, these kind of trees. And then using dimensional analysis, you can kind of guess the regularity of the objects if you could make sense of them, these stochastic objects. So there is a problem, because if you write the equation for V, you find that at some point in the equation for V, it's complicated, but what is important, that involves the product of V with this double cherry guy. And the double cherry guy is C minus 1 minus 0. The V is C1 minus 0, so you have a problem, because the sum of the two is not 0. So I would like to recall, like in the talk of Professor Zhu, she recalled to the audience the Young theorem. If you have two distribution of regularity, Hölder regularity C alpha, C beta, if the sum of the two exponents is greater than 0, then you can make sense of the product. And I think it's called the Young product, from what I understand. So what I mean here is that you cannot make the Young product of the V and of the double cherry tree. The Young product is forbidden. And so a key insight of the work of Jagannath and Perkowski is to find a new parametrization of the solution phi involving a Kohlhoff transform. So you rewrite the solution as this thing here, where you use an exponential prefactor, exponential minus 3 times this guy. And of course, this prefactor is here to kill the ill-defined product between V and the double cherry tree. And in terms of this new parametrization, so okay, I don't know how they came up with this. Looks miraculous, but it allowed us to write this paper. Then the U solves a new equation. And in this new equation, these terms Z0, Z1, Z2, they are of regularity C minus 1/2 minus, and you have a transport term with a singular vector field. Okay. And as usual, in this SPDE business, Z0, Z1, Z2, they depend in a good way on a finite list of stochastic objects that, like Ivan's talk yesterday, are defined by iterated integrals starting from the noise. Okay, so I don't want to go too much into details because there's big integrals to write these things. But physicists can understand when you solve an equation before quantizing, it's given by trees. Okay, and the loops, they come from quantization. So here it's we have trees. But the leaves of the trees are random. The leaves of the trees are these white noise. In the bundle case, we have to introduce a kind of random bundle map. And this random bundle map is local in the sense that it defines C infinity of M module morphism. So it means that, in fact, it takes a section, evaluate section, and it defines a distribution, but everything happens over the same foot point. It's local in some sense. And so using this random bundle map, you can define a vectorial Kohlhoff transform, which extends the Kohlhoff transform defined by Jagannath and Perkowski. And using this vectorial Kohlhoff transform, we can also treat the vectorial case. So the theorem that we proved together reads as follows. If you have a Hermitian bundle over your manifold, 3 manifold, you heat mollify your A. There is a psi missing. The display, he killed my psi. But you know, you heat mollify your white noise with the heat operator, there is a psi missing. Then there are two counterterms, C1 and C2, such that this equation has a well-defined limit when R goes to 0. And for the physicist, I do not pretend I'm a physicist. I just think that I can understand that C1 comes from what you call a tadpole graph, and C2, you see there is a log divergence, so it must come from sunshine. Okay, so this guy comes from sunshine, and we make also the following observation is that these counterterms, they do not depend on the Riemannian metric G. So this is a bit of maybe not a surprise, maybe a disappointment, in fact, because it tells you that the quantum field theory does not fill the background geometry. But then I asked some physicists, and they told me it's not surprising because when you, in the UV, you look at short distance, so you don't see the curvature any longer. So it's no big surprise that your counterterms are kind of universal between quotation marks. And so it means that somehow the solution of your SPDE is defined by a renormalization which has the local covariance property. Of course, it does not depend on the metric, so it's locally covariant. And also Ismaël Bailleul, so the first one, he has recently proved that, so this we proved that it has existent in short time, and also then for all times. And we prove also that this T minus UT dot, or maybe it's a phi. I'm sorry, T maps to phi T dot. This defines a Markov process in C minus 1/2 minus, okay? And the 543 measure is in fact, we proved the property called coming down from infinity for this SPDE. And from this coming down from infinity, we can construct the invariant measure by the classical Krylov-Bogulyov-Bov procedure. And recently, Ismail Bailleul was able to come up with the proof relying on this machinery that the invariant measure is unique. So it's very recent. So he found this proof. He wrote a paper independently. And now in the remaining time of my talk, I would like to describe you in an impressionistic way some new ingredients that we need to set up to construct this 543 theory on manifolds. So first, I would like to say something. We do not aim for generality. We were just aiming at the result. I mean, so it does not have this deep general flavor of some tools that we heard at the conference. It's just ad hoc. Okay, so first, your manifold, we all know you can cover by charts, compact manifold, finite charts. So one of the fundamental tools used in the community, working, following the works of Gubinelli, Perkowski, and Imkeller is paradifferential calculus. And they need to cut some random objects into high modes, low modes, and study the interaction between high, low. You see, so this is called paradifferential calculus. And you first need to make something similar to find an ansatz on manifolds. So we follow the very simple way. You have a partition of unity. And for instance, if you have a product, let's say you multiply two functions. Of course, you can say this is a sum over chi I uv. You use the partition of unity. And once you localize, you use another cutoff function that dominates the chi I. And using charts, you can reduce to the situation on RD. So here, the product here lives on RD. And once you are on RD, you can use the decomposition of the multiplication of smooth function on RD in terms of resonant, paraproduct, and other paraproduct, okay? So this gives you a cheap way, I would say, to decompose multiplication on manifolds as a sum over, okay, some kind of localized paraproduct and localized resonant product. So these objects are not very intrinsic, but they have a very good property. They are easy to define, and it's very easy to check their analytical properties because the Bezov space, they are Diffeo invariant, they are stable by multiplication by smooth function. So every result defined on RD just go through on manifold if you use this, which is a bit cheap. So it's not intrinsic, but it has good analytical properties. And one of the main philosophy that I would like to emphasize, but this philosophy is present already in the Gubinelli, Perkowski, Imkeller paper, is that you kind of, from what I understand, they localize singularity using commutator arguments. So yesterday in Ivan's talk, there was something I like very much is recentering. You know, there was this guy and then there was some motions in the Feynman graph, recentering like algebraic things. And I feel like in this business, the motion, the good motion you need to have in your mind is using multiple commutator to estimate and to localize singularities. Let me give you an example. So at some point in the work, to make sense of this SPDE, you have to treat this borderline product, f of this tree times this paraproduct. And you want to reduce this to some fundamental brick that you were able to renormalize. So your target, so you don't look at the equation. Maybe they might look frightening, don't care. You just look at the beginning, the starting point. I start from this, but I know I control this object. So I want to write this guy in terms of the objects that I renormalized modulo nicer guys. And how do I reduce this guy to something I control, like I can renormalize modulo nicer guys, is by iterating commutator arguments. And so here is just a kind of a toy version. So they use paralinearization, various commutator arguments to isolate the singularity in this term. And this term is treated by renormalization. And so this thing, we were able to implement it on manifolds using exactly the strategy I showed you on the toy model of the product, using charts, DFOs, and flat operations. Okay, the second ingredient, and this is present in all the works in SPD, from what I understood. So in the work in the IROR school or in the GIP school, is that you need to make stochastic estimates. So you have these stochastic objects, these trees, and you want to prove that you want to control their Sobolev norm to the square, in some sense, okay? And this is where objects I'm more or less familiar with, Feynman diagrams, they arise. It's very strange when you work in SPD because you are looking for Feynman diagrams because you were taught Feynman diagrams, this is the thing, this represents the process, and this is the important material. And up to now, we didn't hear anything about Feynman diagrams. And this is something which is very unusual for me, who is a bit familiar with Feynman diagrams. But in fact, here, in this framework, they arise when you do the stochastic estimates. So when you control this quantity, you can control it in terms of a finite sum of mirror Feynman graphs. This is very, very close to what Yvan described to you yesterday. He discussed about this because you have your tree and the leaves are white noise. When you calculate the expectation of some tree to the square by the Wick theorem, it means that you have to glue the two trees along their top leaves. So you see, you have two trees, you glue them along the leaves. So you get a Feynman graph. But why can you reduce to mirror Feynman graph? I think it is a very useful lemma, I think, that can be found in the paper of Eirer. In fact, you can reduce this control to this sum of these mirror Feynman graphs. And contrary to QFT, where the line is the propagator, and the propagator in Euclidean QFT is the inverse Laplacian, here it's very complicated because the lines, they have a weird decoration. It comes from the context, from the SPD context. And also here, the multiplication is not the usual multiplication, is the resonant product, so which is denoted by this big bubble. And so this is very unusual for people used to QFT. So here I wrote for you an integral, but it is not I mean, it's just for the sake of having seen these beasts. I was very afraid when I started doing these things because, okay, so this graph here, it reads as this horrible integral over the configuration space of 8 points in space and 4 points in time, okay? So you see that this, the Schwarz kernel of the resonant product depends on 3 points because it's an operation with two input, one output. So each Schwarz kernel has the 2 ingoing legs and 1 outgoing leg. So it's a Schwarz kernel with three variables, and you have the various propagators involved in the Feynman amplitude. And the question is now to find the exponent, the correct exponent gamma, for which this expectation is finite. And okay, so if you are a QFT expert, you know that the theorem that says that the Feynman amplitude is finite, I think it's called the Weinberg power counting theorem. So okay, so Neil, your business, I mean your mission, if you are willing to accept it, is to prove a kind of Weinberg type theorem for this kind of exotica Feynman graphs coming from SPDE. Okay.
Dyson power counting.
It's called Dyson power counting. Oh yeah, misattribution. Okay. Okay, so Dyson. Okay, thank you. Okay, anyways, so you have, you see this big product that lives on the configuration space of 8 points is a kind of huge product of distribution. And the singularities of this huge product of distribution, they arise as usual in QFT. It's not a surprise when the points they collide. I'm a position space guy. I like also Fourier. I'm in love with Fourier, but here, since I work on manifold, I need to think about the position space point of view. So you see, you need to devise an algorithm. So we devise a recursive algorithm. So for this, we were very much inspired by the seminal work of Epstein-Glaser in the, I don't know, in the, how many it is? 70s, maybe 70s, yeah, Epstein-Glaser, and then perfected by the contribution by Stora, Brunetti, Fredenhagen, and also many other Holland's world. In fact, what they do is that they do a recursive argument by the number of points that are going to collide. First, they have their big amplitude, which is well defined if you remove all diagonals. So you remove all places where points collide. Then you first extend it when 2 points, 2 by 2, they collide. So you extend to diagonals where 2 points collide. Then you do 3-point collides, etc., etc. You make a recursive argument. And at the end, you have to extend, you have to control some object when all the points, they collide together on the biggest diagonal. So it's just a way, it's just a rephrasing maybe of this BPHZ thing, but in a point of view, which is very much a position space and diagonals, okay? So really, and now, okay, so to make an analogy, maybe for those who are familiar with things, this is a bit like analyzing subgraphs that are spanned by 2 vertices and then renormalizing subgraphs that are spanned by 3 vertices, like preparing the diagram. And then at the end, you make the final extension and you define it on the whole configuration space. So to do this, to perform this correctly, yeah. On the edges. Yeah. It's like heat kernel because it's a heat equation. So it's kind of heat kernel. Yes. There is the bubble. It's a good question because then I can go back and we can, the L-1 are like inverse heat operators. So heat kernels. G2 is like square of heat kernels. You know, I can write it for. Maybe for instance, GP is this guy here, and this L-1, I can give the formula. I'm sorry, I can give the formula. L-1, for instance, is an indicator of T minus S. It's better if I write the formula and don't talk. This is the kernel, okay? So yeah, I think it's the heat kernel. That's what you wanna hear. Okay, so, and this is a bit like the green function. It has a scaling degree, but for parabolic scaling. But like in your talk, I mean, if you heat, it's parabolic. You must scale parabolically. So okay, so just to conclude the talk, I just would like to comment on the kind of meta principle behind the proof. Is you have to find a device to measure the singularities of distribution when you approach a submanifold. So in our case, the submanifold is the diagonals, but here it's an abstract result. You have an ambient manifold, you have some kind of distribution, you want to measure the growth along a submanifold, and you want to extend this distribution to the whole ambient manifold. So how do you do this? So there is a geometric way. You construct some vector fields that allow you to scale towards the submanifold. So we call them scaling fields. So they are defined, and it's a class of vector fields defined algebraically using the ideal of functions vanishing on the submanifold. And in 1D, it's just kind of Euler vector field that allow you to scale towards your submanifold. And then we have some theorem that says that if the growth of your distribution, when you scale it, and when you approach a submanifold is controlled in some way, then, so this is something we call weak homogeneity, following the work of Yves Meyer in '98. Then if S, the exponent here, that controls the growth when you approach a submanifold, is greater than minus codimension of Y, then the distribution U admits a unique extension over the whole manifold. And since we work with the Feynman amplitudes, we need to control precisely the singularities of all the objects that arise. And for this, I use a microlocal analysis, the wavefront set. So stuff that dates from the 70s by Hermander. And okay, just in one word, the wavefront set, it controls not only the singularities of distribution in position, but also in momentum. It tells you in which co-direction your guy is becoming nasty. And it is, in fact, it was invented I mean, more or less, maybe I'm not good in history, but it seems to me it was invented to describe, one of the applications is that you could describe the singularity of the Whiteman function in QFT. And you can use the wavefront set to describe the singularity of this is the real two-point function. Euclidean QFT is not the real thing. The real thing is the Lorentz QFT in Minkowski space. And so this wavefront technology was used to define the singularities of a Whiteman function. And then using this microlocal machinery, we can have kind of extension theorem with a precise control of the singularity, of the microlocal singularity of the extended objects. And since I think my time might be over, I would like to thank you all for your attention.